Hello everyone, welcome to another Uiua programming video. Today we're looking at the Advent of Code 2019 Day 6, and this is a classic pathfinding problem, and I think a very good excuse to talk about the excellent path modifier in Uiua, which helps us to very easily solve problems like these. So what we're given is a list with nodes and their connections. So this is a start node and an end node, and you can see that basically it ends up looking like this if you draw out the connections. And what we're asked to do in this first step is count the number of direct and indirect orbits, which you can see we're looking for 42. So basically what it's asking is what is the distance between each of these nodes and this root node, the center of mass. And it gives you some kind of more complex explanation about orbits and so on, but really it's just asking us to find the distance between the root and all of these nodes and then add them together. So we can go ahead and copy the input over to the pad, and I'll work in this full screen today. I think it's going to be a little easier since there's a lot to look at. Before we get started on really dealing with the problem, though, let's look at this path modifier. So it, as it says, finds the shortest path, and it expects two functions and one value. So we need to give it the starting node, and then we need to give it the first function, which will return the neighbors of the current node, and the second function will return whether or not the goal node has been reached. So let's take a look at how we can build what we need for this modifier. So the first thing we need to do, of course, is parse this input. So we'll use our usual approach of the PBBN idiom, which will get us the data from each row. So we're separating by the new line character. And then for each of these lines, we want to separate on this right parentheses character. So again, PBBN, and this time it's the right parentheses. And this gets us our matrix of start and destination nodes. And from here, what we can do is basically get a kind of identifier array that we can use to index and remove these names. We don't really need to work with these names. We can just work with their position in this identifier vector. So we can use by to call a function and make sure that we keep this. We can use reduce to apply a function in between the rows of an array, and then we can use join, and that will get us a list of all of the elements in one vector. And then we can deduplicate this, so now we have this identifier vector. And getting this turned into the indices here is as simple as using the index function. So I can show you if we just use index here, index in, then what we have is exactly what we're looking for. So you can see that the first row is 0, 1 because column is this 0th position, and then B is the first position. So this is exactly what we need in terms of indexing. And the reason we want this list of indices or these pairs is so that we can make this neighbor node function for the path modifier. So what we would like to have is a list where we can say, for example, I'm at index 5, what are all of the neighbor nodes that I can go to from here? So we basically need to group these destination nodes by their starting node. And we can do that by uncoupling first. So if we apply uncouple to each row. That will split the rows. Now we have our starts and our destinations. And then we can use the group modifier, which will use these indices to group this second array, which is exactly what we need. So we can use box, and now we see that from position 0 we can go to position 1, from position 1 we can go to both 2 and 6, and so on. But actually what we need in this case is not moving outwards from the center of mass, but the other direction. So for this one, it would actually be better to group the starting nodes by the destinations. So that's a matter of just flipping the order of this. So we can do that here. When we uncouple it, we'll just uncouple it backwards, and this will put them in the other order. And now we can apply this group and box. And we can also think if we want to work with these boxes or not. Generally, if we can avoid boxing, there can be some performance benefits. So if we try to do ID here without, so we don't box them, you'll see that we have this issue with the shapes not matching, and we can fix that by giving a fill value, and that will fill any shape mismatches with in this case infinity, which won't impact our pathfinding because, yeah, well, pathfinding algorithms avoid infinity. This gets us now our neighbors. So what else do we need then? We can provide the start nodes, that's just all of our nodes, and we need the target though. So in order to figure out if we've arrived at COM, we basically need to check, is my current node equal to this node? So let's get the index position of this COM node. In this case, we know it's 0, but in the real input, we won't necessarily know where it is in this vector. So let's use index again to do that. So we'll put COM on the stack. If we try to index now, you'll see that we don't get what we're expecting, and that's because we're indexing into a list of boxes. So we need to make sure that the needle is also boxed. So we'll box this, and then we'll use back index, and this gets us the 0 that we're looking for. So we need to do both of these things actually on these inputs. So for that we have the fork modifier, which will call two functions on the same values. So one thing that we want to do is build this neighbor list, and the other thing we want to do is get this position. And now we have what we need. So with this now, we can start to look at path. The only thing we don't have is the starting position, but let's just try with an example starting position, a single starting position. So we're starting at position 7. These are our neighbors, and we're trying to get to position 0. So let's look at what we need to give to the path modifier in terms of functions. So the first function needs to return the neighbors. So in this case, we just need to pick this index position out of this neighbors list. So we'll simply use pick. And to check whether we've arrived at our destination for this second function, we need to compare this current node with our final desired node. So we want to use equals, but we need to get around this middle stack item, and for that we have the reach modifier, which, as it says, will call a function skipping the second argument, which is exactly what we're looking for. So if we run this now, you can see that in order to get from 7 to 0, we start at 7, we go to 6, then 1, and then 0. So that is exactly what we're looking for. So we can use first to get this first path, and we can call length because we want to know, well, yeah, the length of it. And now, rather than going from 7, we want to go from all the possible nodes. So we want to go from node 0, from node 1, from node 2, and so on. So in order to enumerate this vector, or this array, I guess, we can use unselect, and this will enumerate the first axis. And from here, now we want to call this same path function, but we want to map it over each of these items, and we want to repeat these two items that are lower on the stack. So we'll use the sided row modifier, and we'll tell it as well at 2. So we're saying repeat 2 of the items on the right, on the bottom of the stack, and this gets us now what we're looking for. But it's important to remember that the path includes the starting position, and we just want the number of steps to the destination. So we actually need to decrement each of these. So we'll just use decrement here, and now we can add the whole thing up, and we get 42, just like we were expecting. So this is our part 1 solution. Now for part 2, what do we need to do here? So we have some new test input. Let me copy this. And it asks us to find the number of orbital transfers between the U node and the SAN node. And it gives this kind of complex explanation about orbital transfers and so on. But basically, you can see we just need to find the length of the path between these two nodes, and then we need to subtract 3 from it because the start node and the destination node both don't count, and we also only need to get to 1 before the Santa node. So it's just find the distance and subtract 3. The other thing to note is that we previously were only moving backwards, and now we need to move both backwards and forwards. So let's do that, build our new neighbor function, and then apply path again. So let's take a look at that. So I'll replace this test input, and now we have our new identifiers, and including the U and SAN. So we'll again need to do this indexing, but now we have start destination. We would also like to have from destination to the start so we can move in both directions. So let's apply reverse to each of the rows. Let's use by to keep the original one as well, and then we can join them together. And I need to scoot this back. It's a bit... hold on. Okay. So now we have all of our directions where we can move. And let's do the same grouping. This time we don't need to worry about reversing this. We'll just have our starts and our destinations. And we'll again do the filled infinity and group ID. So now we can say that from node 0, we can move to node 1. From node 1, we can move to 0, 2, and 6. And you see that because we provided this fill value, all the shape mismatches are filled up with the infinity value. So this gets us our way to pick out our neighbors for any of the nodes. And the other thing we need is the start and the destination node. So in this case, the start node is U, the destination node is SAN, and we need to remember that we need to box both of these, so we use both box. And now we want to do the indexing, but we want to index, we have these stack items A, B, C, we want to do indexing A into C and B into C. So for that we can use sided both. So again, it repeats the one that we're pointing at, and we'll use back index. And this gets us our starting node and our ending node. So now we have what we need. Again, we'll need to put this all inside of a fork so that we can call them both. And this gets us what we're looking for. And now let's figure out what we need to do for our path functions. So I'll again set this up. So the first function, we need to get the neighbors. So we need to pick this index out of this array. And we've already seen how to do this. We can use pick, and to skip this middle stack item, we'll use reach. And in this case, we may end up with the current node being infinity, in which case it will try to pick row infinity out of this array. And in order to avoid that erroring, we'll also give this pick a fill value. So any invalid index that we try to pick will just return infinity. And the other thing is the check if we've arrived, and that's as simple as calling equal to see if the current node is equal to the destination. So this will get us what we're looking for. So this is telling us that in order to get from 12 to 13, we need to step through these intermediate nodes. And as I was saying, we need to get the length of this and then subtract 3 from it to get the answer that we're looking for. So with this, we have our part 2 solution. So I think this is pretty cool in Uiua. We can use this path modifier. It's very powerful and very flexible, so it allows us to easily solve these kinds of pathfinding problems and things that are not traditionally, let's say, viewed maybe as pathfinding on a grid, for example. So yeah, it's something to play around with, something to practice. And I think it's a fun problem because there's also a lot of other ways to solve it. Because if you think about what we're trying to do in part 1, for example, this is actually asking us to solve the transitive closure of the adjacency matrix. So it's quite a bit slower, but it is quite cool to do these kinds of adjacency matrix operations and think about how this is equivalent to different graph theory problems. I'm not going to show that. It's a bit outside the scope, but I guess if people are interested, I don't know, let me know. I can do a follow-up on that. And for this one, you could also do something crazy like employ a Floyd-Warshall algorithm or something and basically solve with dynamic programming all of the shortest paths between all nodes in the graph. It's very unnecessary, but it's fun to practice these different graph theory algorithms at times. But anyway, so yeah, that's the path modifier, and it's pretty performant as well. I can show with the real inputs, it's a pretty big grid. So let me just throw it in here. You'll see it's not going to run instantly, but it's going to run. I mean, yeah, let's say it took, I don't know, 2.5 seconds or so, running in the browser, right? So in native, it runs in well under a second. So I think quite the performance solution. And yeah, just to give you a sense of it, there are, well, I don't know, I'm not going to count them, but there's a ton of nodes, and it's a very big graph. So anyway, I hope that was interesting. I hope you learned something, and I'll see you in the next one. Thanks a lot for watching.